But the S means distance?
The what?
The S means distance?
Yeah.
Okay.
Always you multiply by the reciprocal by multiplying V over theta. So
Start, Giovanni?
like I just realized that you multiply theta over V by the reciprocal, making it V over theta. That's how you got V squared sine theta over.
Yes. Yeah. Dividing by a fraction, say it's multiplied by the reciprocal. Now, on the surface, this doesn't really seem like it's that much better. I mean, V squared sine theta over R theta, we still have this theta, which is somewhat arbitrary in there, so it would be nice if we could get rid of it. What I really want to know is the acceleration at this point right here. In essence, what I've got right here is an average acceleration, but I want to find instantaneous acceleration, so what I want to do is I want to make theta smaller. As theta gets smaller, time gets smaller, well, that relationship right there. And so if we make this theta small enough, then we're finding the average over a tiny little segment, which if it's small enough, we'll call it instantaneous. So now I introduce you to the small angle approximation. It turns out that sine of theta, if theta is in radians, is equal to theta minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial, and so on. That is wrong. Let's try that again. Theta, dang it. Those numbers are wrong. That's cubed, 3 factorial, 5th, 5 factorial, 7 factorial. There we go. Sorry for that. If theta is tiny, then, well, some tiny number to the 7th power is insignificant. Matter of fact, if theta is small enough, all of these are insignificant. So the small angle approximation says that if you're dealing with a tiny angle, if theta is in radians, then the sine of theta is equal to theta. Close enough. And you try it on your calculator, again, theta's in radians, but if you take 0.05, the sine of 0.05 should be somewhere around 0.05. And I believe Robin's about to tell me if this is true or not. What is it?
It's 0.48. Oh no, sorry.
0.048?
Yeah, 0.48. Sorry. 0.48.
So did you do the sine of 0.5? Or 0.05?
0.5.
Okay, so 0.5, the sine of 0.5 was 0.48.
Yeah, and then for 0.05, I got 0.05.
Oh, got it. They rounded off to that.
Yep.
Yeah.
So if we're dealing with a really small angle, then my equation over there becomes my acceleration is negative j hat times v squared theta over r theta, which is just negative v squared over r j hat. The thetas cancel out. Matter of fact, from small angle approximation, we're dealing, so if you imagine the unit circle, if I'm dealing with tiny, small angles right here, cosine is practically 1. So the cosine is approximately equal to 1 if it's really tiny. Sine is approximately equal to the angle in radians. So sine over cosine is approximately equal to theta over 1, and that's just the tangent of theta. And so small angle approximation takes it one step further typically. Sine theta equals tangent of theta. I guess I should do the approximation sign. Remember, all this was developed pre-computers, and so it was, or at that point, computers were people. So this kind of shortcut is very convenient. So what we have here is a simplified equation. If I know how fast I'm going and I know the radius of curvature, the radius I'm taking, I have an idea of what the acceleration is. So imagine you're going around a car. You're in a car going around a curve. If you take a really sharp turn, you run the risk of spinning out. If you're going too fast, you run the risk of spinning out. So if V gets bigger or R gets smaller, it requires much more force in order to maintain that acceleration. Questions here? Now,
I have a question.
yes.
When we do something like this on tests or homework, when we show our working stuff, are you expecting us to essentially show all of the work and how we got from?
Do I expect you to derive V squared over R?
Yeah.
No.
Okay.
No, the main purpose in deriving it is so that you know where it comes from, as opposed to, and then a miracle occurred and here's an equation.
Okay.
Yes, Bikika.
Is there a reason you wrote negative j hat like separate from the rest?
Just because I wanted to not forget the unit vector, and so that's, I was afraid that if I put it at the end like I traditionally do, that I would forget at some point.
Okay. So can we still cancel if it was like in the parentheses?
Yeah. All right. Now, one thing I should have done before I erased. So that was at the peak, and so the negative j hat direction would have been this way. So that acceleration is pointing towards the center. If I had talked about over here, well, I could just adjust my coordinate system so that it looks like that, in which case it would still be pointing towards the center. No matter where I am in the circle, the direction of the acceleration is towards the center. For things where the direction is towards the center of a circle, we have a name for it. That is centripetal or centripetal, depending upon where you're from. Or the traditional which group of Wills ratio. It is not the other one that people tend to use. I will talk about it briefly right now, and then potentially that's going to be the last time we talk about it. Centra, from the Greek for center. I think this is Greek stuff. PET, competition is a word that we have today, which uses that same root. In competition, you have two teams that come together. This is center seeking. So this thing is trying to get into the center. Remember that it wants to go in a straight line. Inertia says that objects want to maintain their velocity, and their velocity is always tangent to the circle, so when I let go, it should travel in as straight a line as possible, except for the gravitational force in my example earlier where it pulled it downwards. So it wants to go that way, but it keeps getting pulled back towards the center. Paraphrasing a line from Godfather 3. Every time it tries to get out, something just pulls it back in. And I wish I could do a decent enough Pacino accent, but I can't. Now the other word that people often misuse, I'm not saying that it can't be used properly, I'm saying that most people misuse it. And so that's why I don't want to spend much time on it. And if in doubt, you probably should not use that word the rest of the class. The course, I should say. And what is the other word?
Centrifuge.
Center. Fleeing. And what word do we have in English? That.
Fugitive.
Fugitive.
Yeah. There's also a Latin expression that I've heard on enough TV shows, tempus fugit, which means time flies. So this is center fleeing. So this would be for a vector that's pointing outwards. Now typically, to use it properly, there's basically two cases that you'd be most apt to use it. Let's say that you're in a car and you feel yourself, it feels like you're getting thrown to the outside. You're not actually being thrown to the outside. What's happening as you go around the curve, your car is doing this, your body wants to go straight, but something's keeping you from going straight. It's the car. So there is a centripetal force pulling you towards the center, giving you centripetal acceleration. Now the fact that it feels like you're being thrown to the outside, this is known as a rotating reference frame. So instead of using the Earth as your reference frame and seeing a car going around the curve, you use the car as the reference frame and you're seeing everything else sort of spinning around you. That is, so if you're in a rotating reference frame, that's one place that you can use this term centrifugal. Some textbooks will just flat out say it's a false force. It just feels like that, but it really depends upon your reference frame.
So what would you say, so you know the swings that are like on a fair where it's like you sit on it and you start swinging around, would that be centripetal or centrifugal?
It is centripetal, that centripetal. Because as it spins around, again, you want to go straight, but something's pulling you in. As you go faster, actually we'll get to the relationship with speed at some point, but yeah, you go up into the air, but you still want to go in straight. If the chain broke,
You go flying.
you're going to go flying in, well, a straight line except for gravitational forces pulling downwards.
So centrifugal is when the reference point is the object that's moving.
Yes, yeah. The other place that you can use it is that as I was swinging the stopper on the string, so there's my stopper, there's the string, it's spinning around like this. The force acting on the stopper is inwards. That is a centripetal force, a little F sub c there. But every force has another force, so if I have my string right here, there's this force of equal magnitude sitting right here pulling the string tight. That is an outward facing force, that is a centrifugal force. But this is usually our concern, and so that is more of a side note. Centrifuges, in my opinion, should have been called centripetes. But I was not asked, and so we're stuck with it. And I'm about to race centrifugal, or centrifugal, and potentially never speak of it again in here.
So,
Do you have a question before I erase it?
yeah, well, so like even if an object is not attached to something at center, like, okay, NASCAR,
Going around, okay.
it would be that they are in centripetal force going around, but if they, so you literally wouldn't have an example like with the rope there of centrifugal.
Okay, but we'll talk about, we'll talk about NASCAR or just going around any curve. It would be, just from the language point of view, centripetal, although centripetal just flows much better for me, but unfortunately it sounds too much like the other one. But they're in centripetal motion,
Okay,
because there's a centripetal force acting on them, causing centripetal acceleration.
okay.
All right, so in the case of, I assume you mentioned NASCAR banked track.
Yeah.
And just a bank track just means that as you're going around the curve, you're not going flat, but there's a bank underneath it as the car's going, in this case, we'll just say away from us. Sure, that's a car. Rear view. So it's going around this curve here. Force diagram. What are the forces acting on the car?
Wait.
Normal force?
Normal force. Friction. No, wait.
Well,
Not for this.
Let's keep it ideal for right now, assuming a frictionless track. However, there is, in reality, there's probably going to be friction unless you're driving at perfect speed. We just don't know whether that friction's acting up or down the ramp, depending on how fast you're going. If you're driving slowly around the friction's acting up. If you're driving fast, the friction's acting down. But there's a sweet spot in between. So, in this particular case, what is the direction of acceleration? It's going around a curve. Hint, it's not down the ramp.
yeah, so it would.
He just, go ahead, I'm acknowledging he said something correctly.
Then I'm gonna not say anything.
Sorry to have stopped it. Why to the left?
Well, I was gonna say that's where usually race car tracks go. Like they usually turn left.
Oh. Given my drawing right here, remember that centripetal forces act towards the center of the circle. The circle that it's traveling in is like this. They're not traveling in a track like this.
Okay.
That's the death gauge, or whatever they call it, the surface. So they're traveling in a circle like this. So my acceleration is in that direction. Therefore, my net force is in that direction. That's my acceleration, is to the left. So part of my normal force, though, is acting at this angle here. Part left and part up. If I set up my coordinate system, which one of these forces are we breaking up?
What are the
Normal. Yeah.
normal?
Part of the normal is the centripetal force, part of it is countering the weight. The biggest mistake I see students do on this is force diagram, they get that far and then they go, oh, acceleration's down the ramp. If you're doing centripetal motion, the acceleration is towards the center of the circle. Let's figure out, let's go ahead and just break it up. So I've got this angle right here is theta. I have normal force going this way, and I need to figure out how much of that is to the left and how much of that is up. So I need to figure out that angle. Now I know that angle is going to either be theta or the complement of theta. Which one is it?
The complement of theta.
Why?
Okay, so I'm imagining it like it's inside the triangle. So it's right angle. Wait, now I'm confused.
Would it help if I said you're right?
Probably.
Okay, you're right.
Oh. Because
But
the
why?
top. So the first triangle, the one with the theta, the top part is the complementary. Since that's the complementary, the other part would be.
This part here?
Oh yeah, no, hold on.
You need to tag team?
Yeah,
Who are you tagging?
whoever wants to join. Well, right.
Someone else want to pick up where he's left off?
If you imagine 3 triangles there, then the complement above the original theta, directly above it, nope, imagine a 3rd triangle. Yeah, so the complement of the one direct, that would be theta prime, which means that the one directly across from it would be, wait, but that makes no sense. Because then you said
Wait, hold
that
on.
angle
So-
in the box would be, in the top triangle would be.
No, that would be a right angle, right?
Yeah, I think you
That's-
got there.
That's a right angle there, that's a right angle there, that's a right angle there.
But from like the ramp, so the ramp and then the line over there is at a right angle too.
Yeah, that's perpendicular.
This is a right angle as well.
Okay.
So that would be theta complement.
Here. Yeah, that's theta complement.
Okay,
So this angle up here is theta.
okay.
I was wondering if you're gonna go, I noticed I drew my angle, looks like more than 45 degrees finally. All right, let's make it more extreme. If that's theta right there, and I have my normal force going this way, and I'm breaking it up into components, one of these angles has to be the same as this one.
Yeah.
Well, that's the big one. That's approaching 90, that's approaching 90, so that's theta, that corner right there. Which means that this right here is going to be the hypotenuse, the normal force times the sine of theta, and this one will be times the cosine. So my force diagram over there now has weight acting down. And let's see if I can actually draw it down. That's better. Weight acting down. To the left, I have y times the sine of theta, and up, I have y times the cosine of theta. This is the only twist that we have on what we've been doing for the past several days. We broke down the decomposition, now the equations of motion. How many equations of motion will I have?
2.
Yep. So let's see, I have to find it over there. So I'll have my I hat equation and my J hat equation. Plug it into F equals ma.
The I hat is y sine theta is equal to mass times, yeah, acceleration through gravity. Wait, no, forgot to say just A, right?
I'm going to put a little c there because it's centripetal acceleration.
Okay.
And my J equation?
It's y cosine theta minus weight equals 0.
Yep. Again, the whole point of having a direction perpendicular to acceleration is so we get a 0 here. Substitution. For what do we have an independent formula?
Weight.
Okay, and
Weight equals